Hi, Ryan.
Hello.
I can't pull it that hard.
So Logan is on a college visit, right?
Yeah, he's in. I think he's visiting Wash U.
Yeah, right.
Yeah. I sent you all the homework, but I'm still. But in my email, I explained that I'm still working on the inversions because they're inversions.
Okay. They inverted you.
Yeah. Um, are are you streaming your webcam? Because all I have is a black screen for you.
Okay. Um. Hmm.
Is it working?
Um.
Yeah, I think I am. Hold on. Let me see. I mean, I show here, and I put people on constant presence.
Okay, it's probably just on my end. I'm gonna hang up and read out.
Okay. All right.
There we go.
Okay, that worked?
Yep.
Okay. Okay. Walter should be here. Okay. Well, the first order of business is a quiz. So I'll let you start. I mean, if Walter's late, that's his problem. uh, Walter left. Okay. That's interesting. I guess he's trying to get on because I just got this message that said Walter left. So let's give it a minute. Meanwhile, you can get up. eCollege, and it's going to be quiz 9, and the password is Euclid with a capital E, EUCLID.
Okay. Thank you.
Walter join. That's cool. He's having trouble getting on. phone number for you.
Can I ask you a question about the quiz?
Yes.
With number 5 about the dot product.
Yeah.
Uh, when we had, you give us the coordinates.
Yeah, that's like a vector.
Okay.
Same thing.
Great. Okay.
Yeah, remember there's a one-to-one correspondence between points and vectors, and so the same thing.
Okay. Hey. I got the multiple choices right.
All right. Good. Are you done? Or you
Yeah.
want more time? Yeah. Okay. Good. Excellent. All right. So it's just you and me today because Walter has had trouble getting on. So that's okay. I'll make a separate appointment with him.
Okay.
So the next thing was going to be questions on the homework. So it sounds like you have some questions on the inversion. Do you maybe it's best if you if we go to Adobe Connect and you share your screen with me on that file? You want to do that or what?
It's
Or you
not
have
so
another?
much that I have questions on like the actually doing the process. I'm just I'm still trying to figure them out. Like I know what I need to do, but I still need to flesh it out a little.
Okay. So you don't need any hints. Is that what you're saying?
Yeah, no.
Okay. All right. Fair enough.
I do have questions when you ask for justifying the dot product. The
Oh, you have
okay.
questions on the dot product handout.
Yeah, I can pull
Okay.
mine up.
Yeah, why don't you do that, and I'll go on Adobe Connect. And I have to share. Hold it a minute. There. So what I have to do is share the screen so that I have to share the correct screen. So hold on. There. Screen 2. Yeah, that's the one I want to share, I think. Yes. Yes. All right. That's for the recording. And now, when you share your screen, I should see it.
Can you make me a presenter?
Oh, right. Hello. Yes, of course. Got it. Sorry, forgot.
Oh, it's fine. It's pulling up the extra app thing.
Okay, right.
Program.
The add-on, right. There we go. Boy, one of my colleagues used to say, technology is great when it works. It's really true.
Yeah. It's still trying to convert all the math type problems.
Okay. I made this handout, for you guys. This is the first time, so it may not be perfect.
Oh, it's fine. Yeah, there we go. 54.
Mm.
With the addition right here. So, right that guy.
Oh, yeah.
Is that actually how it's supposed to come out with just
No. No.
Oh,
It's supposed to be x plus u on top and y plus v on the bottom.
okay. That's what I thought. So I think with most of mine, I have that right.
Let me look at my file. It could be that. Oh, hold on a minute. Let me look at this. That's a mistake. Ha! Shame on me.
We all do it.
All right, x plus u, y plus u. So I'm going to fix that.
Uh,
Here we go. Yeah, okay, I'll repost that. Yeah, so no wonder you're confused about that.
I thought it was like that, but I have like one or two that I need to change then.
Okay. Let me go back here. Yeah, okay.
Yeah, my main question about these justified problems was, do you want me to show like the math of like comparing the two sides of the two sides and then trying to get them to equal each other, or do you want me to use the different laws to show that they come out to be?
Yeah, that's a good question.
Because this isn't a good one because
yeah. So like for A you could do several ways. You could do it geometrically.
Mm-hmm.
Okay, so that's one way. Or you could use vectors and show that if you go to X, let's say, and then add to that half the vector from X to U.
Okay.
See what I'm saying?
Mm-hmm.
Yeah, go to X and then go halfway towards U, then that would do it as well. So there are a number of, so those are two ways I can think of. It's not just, showing that it's 1/2 X plus 1/2 U doesn't really, tell you much.
Okay.
So that's not what you want to do.
Because for most of them, when I got down here, I was basically taking one side of it and multiplying it out.
Yeah. For those, that's right.
Okay.
Yeah.
Great.
Yeah, that's what you want to do for those. Oh, I assigned through what? 5ABC, something like that?
Yeah.
Yeah. Okay. Yeah. Yeah, it's interesting how sometimes the math type, it was centered properly in the document, but then sometimes when you open it again, it gets off. That's just the way it goes. But you can still read it.
It's still useful.
Okay. All right. Are there any other questions on this?
I don't think so. I'll just have to change a few things for the addition.
Yeah. So why don't you make those few changes and send it to me?
Okay.
Later today or tomorrow.
Mm-hmm. And
I'll repost and send a message about the mistake to the other guys.
Okay. On this quiz, we had the question about how to find the area, the probability of the needle drop.
Yeah. I just wanted the just the general method.
Okay, and when I was actually doing the calculations last night for it, I don't think I did it right because I wasn't using the angle at all.
Yeah, no, you got to use the angle.
Would I need to use like an integral?
Yes.
With like a cosine?
Yes.
Okay. That's okay.
Yeah,
I'll,
yeah.
I'll
Your sample space is like for
I just need to use one of these bars, right?
yes,
Or
that's right. And I'm not sure whether the midpoint or the point that's closest to the bar is the best. It might be the point that's closest. Um, but you could probably do it either way, is my guess. So yeah.
well
So you need a distance,
hmm
okay? And then you need an angle, both of those, and they will give you a rectangle on the grid. So one of the axes is the distance, and one of the axes is the angle. And
Okay.
so the sample space will be a rectangle.
Okay. So the sample space is just like the bar, right? Or is that
The sample
wait?
space is the set of all possibilities. Doesn't
Okay.
matter whether it crosses it or not. It's just a way to specify all the possibilities,
Okay. Okay.
right?
hmm
And then the feasible region are the successes. In other
Okay.
words, the area, the points in the distance angle coordinate system where the needle does not cross a line,
Okay.
right? So if you use the line on the left, let's say, as the
hmm
reference line, then then the distance will be either from 0 um, to the next one, the distance between the vertical lines. And the angle is going to be between 0 and pi if you're using radians. Is probably a good idea.
Okay.
So, yeah. And then um, you might. I'm just trying to think of whether the angle. Yeah, if you choose the closest point, um, or the midpoint. I'm not sure. I haven't done this in a while, so one of those two. Sort of think about them both. Um, if you use the midpoint, then yeah, if you use the closest point, then it's never going to hit the reference bar. You only have to worry about it hitting the other line. If you use the midpoint, then that might be more complicated because then you do have to worry about, sometimes it will hit the reference bar. So there are like two situations there. One is hitting the reference bar, the reference line, and the other is hitting the other one. So it seems to me that using the closest point would probably be easier.
When you say closest point, you mean the closest to the reference line?
Yes. In
Okay.
other words, one, unless the needle is parallel, in which case it doesn't matter, either the eye side of the needle or the point side of the needle will be closer to um, the reference line.
Okay.
And you could just specify that point as the distance. In other words, how far you have to go using a parallel line, so to speak, until you first hit the needle, no matter where, no matter which end.
Okay. I was I have to set up that, or I started with thinking that uh, I already had the needle crossing the reference line,
Mm,
and that it was, and I don't know, like just that the distance was going to be the radius of like a half circle that would be within the spacing.
Mhm.
But that's not what we want.
No. The sample space has to include all the possibilities for the needle.
Okay, yeah.
Yeah, you start
Great.
with that. Okay?
Okay, great.
All right, good. Okay. Yeah, it's not an easy problem, but interesting. So that's going to be our last geometric probability problem.
And
Yeah.
last night I was trying to think you said revise the geometric probability problem.
Yeah, if you needed to.
I didn't have those. I don't think you sent them back in my email at least.
Oh, really?
Yeah. So I guess here, let me check again.
Okay, I thought I did, but if I didn't, I'll do it now.
Because if I can do them tonight if you need me to.
Yeah. Okay. Yeah. Why don't you check? And if I forgot, then I'll do it right now.
Nope.
Yeah. Meanwhile, I'll look in my email.
Yeah, the earliest that I have homework sent back from you is for the April 10th homework.
Oh, I might have. Oh, yeah, I did. Oh, jeez. Shame on me. That's right. I did them, and I'm not sure I sent them. I was reminding myself. Good point. Okay. Boy, I got a lot to do here. Yeah. Okay. I'll send you that right after class. Okay.
Thanks.
Sorry.
No, it's fine. I should have caught it earlier because I was doing this last night.
I don't think I sent Walter's either. Okay. Send homework. Yeah, I did it, but I didn't send it. Send homework to students. Sorry. And then repost dot product. And then send.
I gotta do my journal.
Okay. All right. Thank you. What? Shame on me. Okay, so I think I will modify. I posted the homework, but I think I'll modify the homework assignment to say that I made a mistake and fix that. Reassign it. Okay. All right. So what I wanted to do today was the last one of Henry's. So let me close this. And there is in Doc Sharing this document which says matrices and translation.
Okay. I'll pull it up.
Yeah. Stop sharing. Okay.
Okay, I have it up.
Okay. So it says, the shortcomings of using matrix multiplication in the way we've been is that it doesn't work for translations. And did you get that straightened out? Did you realize why?
Is it because we cause usually with uh, two variables. If you have a equation with two variables, you have three terms instead of just two, and one doesn't have a variable with it.
Yeah, that's right. I mean, the image under a matrix is always of the form ax plus by. In other words, a linear combination of x and y, and there's no room for a constant. Whereas a translation is, x plus c, x plus a constant, y plus d.
Okay.
Right? So there's no constant there. It's just a linear combination of x and y. So the problem is solved, and this is okay, I won't say that. This problem is solved if we represent points as 3x1 matrices, like this. Instead of representing points just as x, y, we represent them as x, y, 1. And it'll always be 1. Okay? So, so it seems like that's, not all that useful, but it turns out that it is. So one says, so you're gonna do 1, 2, and 3. So why don't you share your screen on this?
Okay.
To Adobe Connect. There we go. Okay. Yeah. So you're gonna do 1, 2, and 3, and I'll help you if I need to. So one says find a 3x3 matrix M, such that M times xy1 will correspond to the image of xy after a translation by vector VW.
Okay.
So M is going to be a 3x3 matrix. You might, play with this on pencil and paper, I think, first. Or you don't have to. Yeah, you can do that.
My computer screen's not big enough. Okay, so yeah, that guy. Wait, the 3x1. Okay, it'd be that, right? Mm-hmm. No.
No, 3x3.
No. Yeah. Oh. 3x3. Okay, so it's vector.
You're going to want it to be. Yeah.
So VW. So this would end up giving us a 3x1, right?
Yes.
So I can put that in. So
yeah, and you can put in what you want it to be here, and then figure out what the matrix M has to be. So what do you want it to be? You want X to go on to what?
It's V, right?
VW, that's right.
VW.
VW.
So
right.
I want VX right there.
No.
No?
No. The translation by the vector VW.
So it's addition.
Yes.
Right?
Yeah.
Okay. So it'd just be V plus X, right?
Yeah, let's do it X plus V. Yeah. You start with X.
V.
X.
Oh, whoops.
X. There you
And
go.
then y plus v.
Y plus not V.
Oh, whoops. W, right? Yeah.
Right.
And then I guess I just want 1 at the bottom again, right?
That's correct. Yes. So now, fill in your matrix on the left so that that works.
Wait a second.
Yeah, you don't have to look back previously. Now it's just a matter of you don't want V there
Oh.
because when you multiply, you want to wind up with X plus V.
Okay.
So what times X? This is going to multiply X, right?
Oh, so just 1?
1, yeah. 1 times X plus what times Y. So go over it horizontally. Yeah, the next one. Yeah, right.
So
What times Y?
0.
Right.
No. Yeah.
0, yes.
And then
And the next one, what times 1?
1.
That'll just give you 1. You want X plus V.
This one will be multiplying against 1, right?
Yes, it will.
So 0?
That would just be X. You think about the matrix multiplication. 1 times X, you got 1 times X plus 0 times Y plus what times 1 is going to give you X plus V.
B.
Yeah, that's right.
Oh, forgot about the B. Okay, so I went 0 in that one.
Mm-hmm.
So this one will be multiplying by 1, and then I want a W.
Right.
Okay. So I just want 1 on the bottom. So
Yes. So now you're going to get 1. Yes. Yes. Yes.
Okay.
Okay, close it. That's correct.
Am I multiplying these, or should I put a plus sign in between them?
No, you're multiplying. Yeah, that's matrix multiplication.
Oh,
Yes.
okay. Okay. Cool.
Right. Yeah, that works, right? So with that XY1 in there, we can do translation.
That's cool.
There's your translation, right? Okay. And then problem 2 says find a 3x3 matrix for these various things. So there are 3 separate problems here. Yeah.
Okay.
One is rotation around the origin by angle theta. So for that, you have to remember what the rotation matrix was. You've done that before.
That was cosine theta, and then negative sine theta, and then we go to the bottom, sine theta and cosine theta.
Yes, that's right. So that's what you want to wind up with. So this is going to be, yeah. So you can modify if you want. You can. I'm wondering if copying and pasting your previous answer, because it's got the right dimensions, and then changing the entries. Will help, or you can start from scratch, either, however you want.
Yeah.
You want to copy the whole thing, the whole bloody thing. Oh no, I wouldn't. Oh, I see. Did you copy and paste already?
Yeah. It's down there.
Oh, you did. Okay, fine. Sorry. Yeah. So what do you want? What do you want there?
I want cosine theta.
Well, no,
Plus.
this is going to be your actual answer. So,
Oh,
you have
x
pencil and
cosine.
paper?
Yes, but wouldn't it be x cosine theta?
Yeah, that's right.
And then plus, or minus,
Yes,
no?
that now you got it.
Wait, wouldn't it would just be plus, or x sine theta, right?
Yeah. Is it plus or minus?
I think it's plus because you would have to go down to the bottom row, which is plus.
All right, let's see. Cosine, the actual is cosine. I'm trying to not rely on my memory. X cosine theta. Is the plus in the first row or the second row?
I think it's in the second row for
Okay,
the
so it's
translation.
cosine and then minus sine. And then if you do that by xy, yeah, then that means it's x cosine theta minus y sine theta.
For
And
the
you
first one?
multiply first one. And minus, I think.
Okay, yeah. I was getting my I was multiplying wrong. Whoops.
Yeah.
Thank you. So then this would be x sine theta
Right.
plus y cosine theta.
Yes. Yeah. Let's
Then I just
check that with an yeah, okay. Yep. I was just going to check it with a simple angle, see whether it worked. But
here
yeah,
it is.
you can look back. Yeah, cosine minus sine and sine cosine. That's correct. Yes.
Okay.
Right.
Great. Okay.
Okay.
So,
So now you have to modify the first matrix to make that happen.
Okay. So this would go. So I would want this one to be cosine theta, right?
Yes. Right.
And then this one, I would want it to be. No. This one would want to be cosine of theta as well, right?
No, because this is what's going to get multiplied by y.
Yeah. Oh, I'll do that in the next row.
This is what's going to get multiplied by y. So what gets multiplied by y?
0 in this one.
No, you have a y term.
Minus sign.
Minus sign, that's right.
Then this would be 0.
Yeah.
Then I go down here. So I'm multiplying by x. So I want sine theta.
Mm-hmm.
Then I would like cos.
Mm-hmm.
Yeah, cosine
Right.
theta. And then 0.
Mm-hmm.
So 0, 0. Yeah. I think that's it.
Yeah. So if it's not a translation, so you can look at that pattern and see that basically you're just putting the usual 2x2 matrices in the first 2 rows and columns, and then the third one is just 0, 0, 1, 0, 0, 1.
Okay.
Right. So it's just a silly extension that doesn't really do much for you, except when you're having translation, and it enables you to do translation. Otherwise, it's like a subset that just kind of fits in. Does that make sense?
Great. Yeah, it does.
Okay. All right. And now, yeah, dilation.
Hmm. So I can copy this again. So centered at the origin was factor k. So each one. So I would want kx
Mm-hmm.
and then ky
Mm-hmm.
and then just one.
Mm-hmm.
Okay, so 0, 0. And that would get me that.
Yes, that's correct.
Cool.
And then C.
Reflection. Wait, reflection in the y-axis? X.
X. In the x-axis.
So x would remain the same, but y would be the opposite.
Mm-hmm.
So I have 1, 0, negative? Yeah.
Mm-hmm.
And that guy.
Right. Good. Okay. Okay, 3, the last one that I want to do today.
Okay. Find a sequence of 3 matrices
Mm-hmm.
L, M, N such that N, M, and L times that will correspond to the image of XY after a rotation uh, around point PQ.
Mm-hmm.
Remember? Okay. Written from right to left in multiplication.
Right.
Okay. Okay. I think I got this.
All right.
So, oops. I'll do this guy. So that would be my result.
That's not your result. That's your.
That's my thing right before the result.
Yeah. You have to multiply by 3 matrices on the left. Yeah, that's right. And this time it's going to be it's going to be hard to figure your result. I would suggest that you just do the multiplications on the left and remind yourself of. But yeah, it is going to look like that.
Yeah.
But do the multiplication on the left, and so the first matrix. So you want a 3 by 3 matrix on the left of XY1.
Yeah, and I would want that to be the translation.
That's right.
To the origin.
That's right. Exactly.
So
in the previous part, you already did the translation
PQ.
by PQ, yeah, and so you want to do the same thing except by the VW translation, and you want to do the same thing except this time you want it to be, as you said, minus P minus Q.
Let me just go look at that one.
Good idea.
Okay, so, but I want negatives on those.
Yeah.
What? So 0, 0. Oh my gosh. Negative P. 1, and then negative Q. 0, and then 1.
Right. Okay. And then
And then
the one on the left of that is your rotation matrix, which you found previously.
Okay, so what? Which one? Oh. Let me just go back down to the problem. Oh, so it's just, okay. So I can just copy that, basically.
Yeah, right.
And
Right.
then I just do the opposite of this.
Right.
Okay.
Right.
Now the fun stuff.
And you'll get your answer, which you don't have to worry about. You can do it if you want, but it's not. But yeah, so that's the deal.
Okay.
Right. And then if you did all that matrix multiplication, or a computer can do it for you, you get your result of that you want, which is rotating theta degrees around PQ. Okay. So I wanted you to do 1, 2, 3. And I didn't require, it just said find those matrices, so you don't have to multiply them out. That's good.
Yeah.
What you did is fine.
I pasted them in the wrong spot, and then it messed it up a little, so there we go.
All right, you got it. Okay. The rest will be homework.
Okay.
Okay, so we got that. Good. Now we have not much time, so I'll just start a little introduction. So now I'm going to, you should
I'm
stop sharing your screen.
Okay. Here you go.
Okay. And I'm sharing mine. So let me get up. Here. Oh, I have to go to a different, here. There we go. So I put reference links in a document with these links in doc sharing. And I was going to get a little farther, but that's okay. So we're going to start, you and Walter more or less had the same preferences, although you were in different orders. But the idea was different geometries. You'd rather do different geometries than do more of this linear algebra stuff. And you'll get the linear algebra when if you take a linear algebra course in college, which is the next one after you've taken your calculus. You may want to, I don't know whether you'll want to, you took the calculus AB you're taking, or the BC, you're taking BC, right?
Mm-hmm.
Okay. So the next course after BC is linear algebra, usually. Along that math track, there's of course statistics, that we can also do. So you'll what we've done, I think, will help you at the beginning of that course.
Yeah.
But you wanted to do other geometries, and so including projective, and they all kind of fit together. So I found this Wikipedia introduction, which is pretty good. And then I don't know a great deal about this, so I just ordered a book to help me give you guys some exercises. They'll come tomorrow. But I read this beginning thing, and I want to go over it with you quickly together. And this is really a good page. Of course, it has all these links and stuff. But it refers to Yeah, let me do this first. This is Euclid, a nice modern version of it. This was written 3,000 years ago. And I wanted to show you that the definitions.
Oh, I'm just getting closer. Sorry.
The definitions that Euclid had were really, it's not perfect. So he defined a point in a ridiculous way in a line and stuff, and these are now undefined terms. But a lot of them were reasonably good definitions. But then the interesting part, after all these definitions, was the postulates, and he just had 5. So this says you can draw a straight line from any point. You can join any 2 points with a segment. But this is the crucial one here. And this is to produce a finite straight line continuously in a straight line. And that means that a straight line can go on forever. And that turns out to be an important assumption, as you'll see later. And then these are all pretty simple, right? These are just one sentence, to describe a circle, to make a circle, in other words, with any center and distance, radius, all right angles are equal. But then there's this guy, which is basically the parallel postulate, and it's 5 lines. And that troubled people. And there were lots of attempts to prove this, because why should this one be so much more complicated than the other? So throughout history, there was lots of attempts to prove this. And the fact that it couldn't be done is what led to non-Euclidean geometry. So back to this. So non-Euclidean geometry is geometry is based on axioms that are closely related to Euclidean, but it relaxes some conditions. And there are 2 conditions, and some of these are pretty complicated. But basically, there's a intersection of what they call metric and affine. So metric geometry means that the distance, you can change the distance between 2 points. And there's something called taxicab geometry that does that, where suppose you were on a grid of streets, and then the distance between the only points that, no, that's not true. So the space is the streets. You can't go off the streets. And the distance is how you drive. It's not the straight line distance anymore. So you can change the way you define distance to make a different geometry. That's one way. And then the other way to change it is this, to change the definition of parallel. So, or not to change the parallel postulate, not the definition. So non-Euclidean geometry arises when either the metric requirement or the parallel postulate is replaced with an alternative one. Okay? So in the latter case, one obtains hyperbolic geometry and elliptic geometry. When the metric requirement is relaxed, then there are complicated other ones that we're not going to talk about. That's too hard for now. And Euclid's 5th postulate is the parallel postulate that I just showed you. And that's equivalent to Playfair's, which just says through any point outside a line, there is one and only one parallel line that can be drawn within a 2-dimensional space. So that's what that says. Now, if we relax this, then there are 2 possibilities. That in hyperbolic geometry, there are infinitely many lines through A, through the point not intersecting L, while in elliptic geometry, there are no parallel lines. So there are either an infinite number of parallel lines or none. Now, this is another way to describe it, which came up with the history, and we'll see this in a minute. But another way to describe the differences is to consider 2 straight lines. A picture is better. So I'll go back up here. So in Euclidean geometry, if you have one line and you draw two lines perpendicular, they'll be parallel.
Yeah.
In elliptic geometry, if you draw two lines perpendicular, they'll meet because any lines meet. And in hyperbolic geometry, if you draw two lines perpendicular, they won't meet. And in fact, there'll be a number of them that won't. So that's one set of parallels, but there'll be lots more, not just one.
That's kind of weird.
Yeah, I know it's weird. And how did this come about? It came about by the debate that eventually led to the discovery began almost as soon as Euclid's work was written, because they sought to prove the parallel postulate. That's just what I said. And for at least 1,000 years, they were troubled by that disparity of the fifth postulate being so much more complicated than the others. And they believed that it could be proved from the others. And they attempted to find a proof by contradiction. And there were many people who did that. And what happened was, and it wasn't until like the 18th century, the 1700s, when people really got serious about it or made some progress. And they started looking at quadrilaterals. And Saussure quadrilaterals are, and they gave the first few theorems. So I'm going to click on this. And Saussure quadrilaterals are like this. It's a quadrilateral with two equal sides perpendicular to the base. So you have a base, and you make two right angles. It's just like what we showed you turned sideways before. But the difference is now we make two equal sides. Now in Euclidean geometry, this is of course a rectangle.
Yeah.
Right. But because these angles are right angles.
Okay.
But Saussure was able to prove by avoiding the parallel postulate, which he wanted to do, that you had two situations, that these two angles were equal. They had to be equal. He could prove that in neutral geometry, but he couldn't prove they were right angles. So he just kept going and say, okay, they could either be both obtuse, which looks like this, or they could be both acute. It kind of looks like this. Okay? And this was all very abstract because, when you draw it on paper, that's not true.
Yeah.
So those sides were called the legs, and the top was called the summit. This part was called the summit here. Okay, so are the summit angles right angles, obtuse angles, or acute angles? As it turns out, when the summit angles are right angles, the existence of this quadrilateral is equivalent to the statement, is equivalent to Euclid's fifth postulate, parallel postulate. If those are right angles, then we're in Euclidean space. But when they're acute, this quadrilateral leads to hyperbolic geometry. So this situation is hyperbolic geometry. And when they're obtuse, the quadrilateral leads to elliptic geometry here, but other modifications have to be made to the postulates because, remember I pointed out postulate 2, the straight line can be extended indefinitely. Well, in elliptic geometry, that's not true. That's one of the modifications that needs to be made. You can't extend straight lines indefinitely. They come back on themselves. That turns out to be a consequence of this assumption. So you have to make other modifications. And for that reason, hyperbolic geometry was the one that was looked at. Oh, I'm late. Oh my God. Okay, that was that looked at a lot more than this. Okay, so that's an introduction, and we'll continue that next time. We're out of time. Sorry, I didn't notice.
Oh, that's fine.
Okay, so I'll see you next time, Ryan, and I'll send and make modifications to the homework.
Okay.
All right, we'll see
I'll
you.
work on
Bye.
the inversion. I'll work on the inversion to get it to you.
Okay,
All right. Have a nice day.
you too.